On July 8th, 2026, at 6 in the morning, Universal Time, a 77-year-old amateur astronomer pointed his telescope at the constellation Ursa Major. Just routine, just another night of observation. What he saw should not have been burning that bright. A star had exploded. That by itself is not rare. Stars explode in our universe all the time, somewhere out there, far away. The rare part is something else. This star was supposed to flare up, reach its peak, and start fading, the way every star of its kind does. By the book. By a formula astronomers have known for 100 years. It didn't fade. It kept getting brighter, day after day. Brighter than the theory predicted. Brighter than a star of its class should physically be able to burn, by every known law. And right now, while you're watching this video, somewhere in observatories around the world, astronomers are still arguing about what they actually saw, because there's no answer yet. It's supposed to come any day now. Maybe it already has, while we were still editing this video. This is the story of a star that refused to die on schedule. To understand what happened next, you need to meet the man who saw it first. Patrick Wiggins isn't a professional astronomer working out of some observatory with $1 billion budget. He's an amateur, the kind of person who points a telescope at the same patch of sky, night after night, simply because he can't stop. That night, his target was NGC 3310, a spiral galaxy roughly 45 million light-years away. At first glance, just another unremarkable dot among thousands of others. But this galaxy has a history. Over the past 50 years, 3 supernovae have already flared up inside it. In 1974, 1991, and 2021. 3 stellar deaths in half a century. That's a lot. Too many for an ordinary galaxy. Scientists believe the cause is an ancient collision with another galaxy, one that triggered abnormally intense star formation inside NGC 3310. It manufactures stars on an assembly line, which means, in there, stars die on an assembly line too. Wiggins caught the 4th flash. It was given a technical name, SN 2026SQF, one of thousands of supernovae recorded every year. By every rule astronomers know, this star had one job left: to rise, peak, and quietly fade away. It had no intention of following the rules. To understand exactly what rule this star broke, you first need to understand what should have happened inside it. A massive star spends its whole life fighting gravity. Eventually, it loses. Its core can no longer hold itself up, and in a fraction of a second, it collapses. The outer layers tear outward in a monstrous shock wave. This is what we call a Type II supernova, one of the most studied, most predictable catastrophes in the universe. This kind of catastrophe follows a formula. Knowing the distance to a galaxy and the type of supernova, astronomers can almost always predict, in advance, how bright it will get at its peak. For NGC 3310, that ceiling was already known, roughly 12th magnitude. SN 2026, SQF, was supposed to climb toward that number, hover near the peak for a few days, and begin to fade. Exactly like the 3 supernovae before it, in that very same galaxy. It didn't stop. And by the time astronomers noticed just how far past that ceiling it had already climbed, the numbers coming in were no longer making sense. Something was adding energy to this explosion that the formula never accounted for. What that something is, that's where this story gets strange. That's exactly what happened here. July 10th. The brightness reaches almost 13th magnitude. July 13th. The star has already broken through the predicted ceiling of 12th magnitude, earlier than it should have. From there, it only accelerates. The 14th, the 19th, the 20th. The brightness keeps climbing, as if the star had run out of script and started improvising. By the end of July, SN 2026 SQF had become the brightest supernova of all of 2026, outshining everything that had flared in the sky since January. And it still hadn't fully stopped. Now look closer. Astronomers tracking the star's spectrum notice something else. The color of the flash is slowly shifting, the temperature dropping slightly as the star climbs toward its peak. On its own, that's normal behavior for a supernova approaching maximum. But the scale of the deviation from the predicted brightness, that isn't. That's not what the textbooks describe for a Type 2. There's one class of event that could explain output this far outside the formula. A hypernova. Not a certainty. Not yet confirmed. Just the one hypothesis extreme enough to fit what the numbers are showing. And if that hypothesis is right, what's left behind at the center of this explosion might not be what anyone expected. A hypernova isn't just a brighter supernova. It's an entirely different physical scenario. One hypothesis is that it isn't an ordinary massive star collapsing at all, but a giant star pushed right to the edge of what's physically possible. And instead of a neutron star left behind, the collapse could leave a black hole. The energy released is several times greater than anything a normal explosion produces. This is rare enough that most astronomers see something like it only a handful of times in an entire career. And here's the strangest part of this whole story. Even now, no one can say for certain what actually exploded in NGC 3310, an ordinary supernova that simply refused to follow the textbook, or a hypernova, one of the rarest events in the universe. Proof that our models of how massive stars die are still incomplete. Either answer changes something, but before the numbers settle it, there's a bigger question worth sitting with. What does an explosion like this actually mean for us? Think about what's actually happening out there, 45 million light-years away. Every heavy atom in your body, the iron in your blood, the calcium in your bones, was once thrown out by an explosion exactly like this one. The flash we're watching right now, in NGC 3310, is a factory. And at this very moment, it's scattering new matter across space. Some of it might, billions of years from now, become someone's blood, someone's bones, on some other planet, around some other star. We're not just watching a star die. We're watching the workshop where the universe's future matter gets made. And we still don't know, not for certain, exactly what kind of workshop this is. One thing is certain. Somewhere out there, in the arm of a distant spiral galaxy, a star that was supposed to quietly fade away on schedule refused to do it. And as long as it keeps burning brighter than it's allowed to, all we can do is watch and wait for its last word. The universe keeps breaking its own rules like this, more often than you'd think. If you want to be there when the next one does, subscribe to Star Voyager and come along for the ride.